Right, so in 10.4, we're looking at a different way to talk about events. So we looked at independent and dependent events with the conditional probability stuff. Now we're going to look at something called mutually exclusive and overlapping events. So the first stuff, the independent and dependent, that's when we're looking mostly at probabilities of one event happening and another event happening. Now we're going to look at probabilities of one event happening or another event happening. That or situation is called the union of A and B. The and situation, which we looked at before, this is called the intersection of A and B. Unions or intersections, the and or are called compound events. And that's when multiple events are happening, not just one event. When we want to find the probability of the or situation, we need to know if there are anything in common, if that A and B situation is possible. We have two words for this. Two events are called overlapping if they have outcomes in common, and they're called disjoint or mutually exclusive if they don't have outcomes in common. So what does that mean exactly? So let's look at a situation. So for example, let's say event A is I roll an even number on a dice. Event B is going to be I roll above a 3. So my possibilities for A is I can roll a 2, I can roll a 4, I can roll a 6. I'm going to put that in a circle. For B, I can roll a 4, I can roll a 5, or I can roll a 6. Notice how the 4 shows up twice and the 6 shows up twice. So if I roll a 4, I'm satisfying A and I'm satisfying B. If I roll a 6, I'm also satisfying A or B. And so those things actually belong in the common place between A and B. So I'm going to redraw this using a Venn diagram, right, where I should put the things that only happen for A, which is 2, and only happen for B, which is 5, on their own. But 4 and 6 happen for both, so they go in that little middle bit. That's the intersection. So this bit, that's the A and B's intersection. And then all of this is the union of A and B. So in this case, since we have things in common, 4 and 6 are in common, these are overlapping events. And you can kind of really see that physically in the Venn diagram. Those two circles are overlapping. If I change the situation now, let's say A is I roll an even number, and B is I roll an odd number. Well, now for A to happen, I can roll a 2, a 4, or a 6. And for B to happen, I can roll a 1, 3, or 5. Well, there's nothing in common. So even if I make these circles overlap, it's going to be empty in that overlapping bit. So these are called disjoint events or mutually exclusive events. When we find these probabilities, we want to calculate, it's going to be slightly different. So let's go back to the rolling even and rolling above a 3 situation. Roll above 3. So in this case, I'm going to redraw this picture. 4, 6, 5, B. Okay. So if I want a probability that I get A or I get B, well, I get 1, 2, 3, 4 things, right? So probability of A or B, there are 4 different things that could happen. I can also roll a 1 or I could roll a 3, but that's in neither A or B. But there are 6 total outcomes from rolling a dice. 4 of them are what I want. So 4 out of 6 is what I should get. Now let's try to come up with a formula for this. If I want A or B, I want to find something I can do with the probability of A and the probability of B. Let's start with adding them up. So just A, I have 3 different situations, right? I can roll a 2, 4, or 6 out of 6 things that I could roll. For B, I can also do 3 out of 6 things to get that to happen. But when I add these up, I get 6 out of 6, but that's not 4 out of 6. Right? It's not always possible. And here's the catch. When I'm counting for A, I counted 2, 4, and 6. I counted 3 things. For B, I counted 4, 5, and 6. Again, I counted 3 things. But I counted 4 and 6 twice for both of them. But when I'm rolling a dice, I'm only rolling 1, 4 or 1, 6. And so I'm counting that thing in the middle twice. So I need to get rid of that. I can't count it twice, so I'm going to subtract it. Right? Subtract those two things. And now I get 4 out of 6. So this formula is how we calculate probabilities for these OR situations. For any time, right? Even if it's overlapping, if it's disjoint, if there's nothing in common, then you'd subtract 0. But when there are things in common, you need to subtract it so you don't double count. Because otherwise, when we're counting those middle things 2 different times for each circle. When it's disjoint, it's just subtraction by 0. And so then it's just minus 0, so then that goes away. It's just P of A plus B of B. So let's do an example with this. These examples have to do with card decks. So I'm just going to explain the setup of a card deck. So you have 52 cards. In that you have 4 suits, which are hearts, diamonds, clubs, and spades. The hearts and diamonds are called red cards. These are red. And the clubs and spades are black cards. And then for each of them, you have 13 different cards. You have 2, 3, 4, 5, 6, 7, 8, 9, and 10. Those are the number cards. And then you have Jack, Queen, King, and Ace. These are called face cards because they have faces on them. So 13 cards, 4 different types. So 13 times 4, you get 52 cards. So now we have a card selected from these 52 cards. We want to know the probability that it's either a 10 or it's a face card. So event A is we get a 10. Event B is that we get a face. So to get a 10, there are 4 of them. We could get a 10 of hearts, a 10 of diamonds, a 10 of clubs, or a 10 of spades. The probability to draw A is 4 out of 52 cards. To get a face card, we have 4 of every type. So we have 16 of these. I have a jack of hearts, a queen of hearts, a king of hearts, an ace of hearts. I have a jack of diamonds, queen of diamonds, king of diamonds, ace of diamonds, jack of clubs, queen of clubs, king of clubs, ace of clubs, jack of spades, queen of spades, king of spades, ace of spades. In all of that, I don't repeat anything, right? There's no 10s that show up as face cards, and there's no face cards that show up as 10s. Because of that, we have nothing in common, no common outcomes, which means these are disjoint events. And so when I'm calculating the probability, I just need to add them up. So I go 4 out of 52 plus 16 out of 52, which is 20 out of 52. And I divide that out. 20 out of 52, that's about 0.38. Let's look at the next example. So now we're picking either a face card or a spade. So again, for face cards, we have 16 of them out of 52. For spades, well, we have 13 cards of every type, so we have 13 spades. But now we have some spades that are also face cards because we have a jack of spades, a queen of spades, a king of spades, and an ace of spades. And so 4 are common, right? 4 cards in common. So that's probability of A and B is the 4 cards that we have in common out of the 52. And so now when I calculate this, I go 16 out of 52 plus 13 out of 52, and then minus 4 out of 52. Because that 4 is in the 16, but it's also in the 13. So I need to remove one set of them away. So I get 25 out of 52. And I divide that out. And I get 48%. So hopefully that is clear, looking at like when things are in common and when things are not in common. When things aren't in common with them, then it's a very straightforward add the probabilities up. If there are things in common, just add the probabilities up, but then subtract out the things that are common. The last thing I want to show you is kind of putting all of this stuff together and thinking about where these probability things get used a lot and why probability and stats get related, and how this is used in the real world in an application scenario. So a lot of times, like the examples we've done, these are things that are mostly related to games and stuff that isn't really consequential, right? Like rolling a dice, flipping a coin, probably not very important, meaningful, life-changing events. But there are a lot of applications that people use every day that is very life-changing and very things that like really affect a lot of things in the world. So one huge place that we use probability and stats is medical testing. So when people have diseases, we want to have tests that diagnose them, right? We want to make sure the diagnosis is correct and then give them treatment if they need it. And if they don't have a disease, we don't want to accidentally tell them they have the disease and put them on treatment for no reason. And so we want to make sure tests are accurate both ways, right? We shouldn't be telling people that they have a disease that they don't, and we shouldn't be telling people that they don't have a disease if they do have a disease. And this is where testing comes in. Tests are never usually 100% accurate because people are varied and tests are varied, and it's hard to be really accurate with these, especially for the cost, right? So you could probably make tests that are super, super accurate, but are really expensive because they're so accurate. And people can't afford that. So we try to figure out like what cost point is good enough, right? Like where is it good enough to say we're accurate at a cost point that people can afford? And this varies based on the disease. If it's something life-threatening, we probably want to be really accurate about it. If it's something that's like a 2-day thing that you'll get over for the most part and it's not really going to affect too much, then yeah, like even if it's not super accurate, right? Like maybe if it's just like a really small cold, yeah, like if I told you had a cold and you didn't have it, it's probably fine. Or if I didn't tell you had a cold and you had it, it's also probably fine. Like you'll probably get over it anyway. But if it's like cancer or something, you want to know, right? Because then you need treatment for it and you want to make sure that you recover from it. And so that's where like when it's a much more serious disease, then we think about how do we actually make sure those tests are really accurate. So this is an example of a thyroid disorder test. So this says that we know about 10.9% of the population has a thyroid disorder. And a lab has developed a test to diagnose this. The test is accurate 96% of the time for people who have it and 99% of the time for people who don't have it. So what does that mean? That means that if you had if you had the thyroid disorder and you took the test, there's a 96% chance that it will say you have it, but there's also a 4% chance that it will say you don't have it, even though you do. And the other thing is if you don't have it and you take the test, 99% of the time it will say you don't have it, but 1% of the time it will misdiagnose it and say that you have it, even though you don't have it. So ideally we want both those things to be pretty accurate, right? We don't want to tell people they have the thyroid disorder if they don't, because then you'll probably give them medication for things that they don't need, and that might mess things up and create a new problem. And you don't want to tell people who do have it that they don't have it, because then they need medication and you're not giving it to them. So let's look at how do we know overall if this diagnosis is accurate or not. Because they're two different situations, right? There's a situation where you have it and it tells you you have it, and there's a situation where you don't have it and it tells you you don't have it. So we know that in general, this is where we're going to combine a lot of things we did in probability together. So we're going to start off with a tree diagram to look at all the possible outcomes. So we know that the population, right, that's our starting point. We know 10.9% of people have the disorder, have thyroid disorder. And so that means 89.1% of people don't have it. Then we know that if you have it, it's 96% accurate, which means 96% of the time, it'll give you the correct diagnosis. 4% of the time, it'll give you the incorrect diagnosis. And if you don't have it, 99% of the time, it'll be accurate and tell you you don't have it. But 1% of the time, it'll be inaccurate and tell you you have it. So first we want to know, what is the probability that we have it and it's accurate. So now for an AND situation, we multiply. So we're going to multiply 0.109 times 0.96, right? So this is the probability that we have it and it's accurate. So when we have the AND, we multiply and we get 0.105. Then we can multiply all of these and get the probabilities for all of these AND situations. So this is have and inaccurate. And when I multiply that out, I get 0.004. Then I want the probability that I don't have it and it's accurate, which is 0.891 times 0.99, which is 0.882. And then the probability that I don't have it, but it tells me I have it, so it's inaccurate, which is 0.891 times 0.01, which is 0.009. So I have all of these probabilities of the 4 different situations I could come up with. These are all AND probabilities, so I multiply. Now the next thing is I want to know the probability of an accurate diagnosis. For it to be accurate, I can either have it and it tells me I have it, or I can not have it and it tells me I don't have it. This is an or situation, so that means I need to add probabilities. So I'm going to add the probability that I have it and it's accurate to the probability that I don't have it and it's accurate. And between these, there's nothing in common between them, right? There's no way I could like have it and it be accurate and also be common with me not having it, right? I either have it or I don't have it. So there's no way I can have something that would be in both categories. So I just need to add these two up. So have it and be accurate is 0.105. And I don't have it and it's accurate is 0.882, which adds up to 0.987, which means there's a 98.7% chance that this diagnosis is accurate. So if this test tells me something, I can trust it 98.7-ish%. And then that, once we have this probability, this is where stats comes in, because now we use stats stuff to think about, well, is 98.7% good enough? And that's what you'll learn about more if you go into a stats class in college or AP stats, really thinking about like once we find these probabilities, is 98.7% a good enough probability that we should like actually start producing this test and selling it to people and giving it to doctors and having them use it, or is it too inaccurate, right? Like, and that's where we think about cost, we think about seriousness of the disease, right? Some tests we probably want it to be like 99.9% accurate. Sometimes 95% accurate could be okay. And determining that percentage is where stats comes in. So hopefully this gives you a good overview of like all the probability stuff that you've done in these 4 sections, all kind of coming together in one problem like this that gives you a very realistic scenario of things people do actually. Like this is a pretty straightforward thing that like actually does happen in a lot of scientific and medical applications. So hopefully this was helpful, and this will be the end of this week in terms of videos.